Hello CTM students, my normal voice is more or less back. Welcome to the lesson for 14.4. We're talking about trees today and how that applies to graph theory, and so we're going to learn about these four little bits of vocabulary there. Not quite as much in this one, but still very applicable, very interesting stuff I think too. So let's get right into it, into our first example. We've seen something called family trees before. I would imagine you've seen something like that. And so this first example is actually going to use a family tree and show you how it connects to the idea of trees as it pertains to graph theory. So let's say that John has 3 children. And John's 3 children have names of Jose, Lee, L-I, and Divjo. It should be a period there. So this is a very diverse family, we're going to say. We've got people of all kinds of ethnicities in this family. There's the Bell. Hello, Bell. How you doing? How you been? Haven't heard you in like 7 minutes. Jose has 2 children. And Jose's children are Crystal and Mohammed. So he decided to continue the diversity. Maybe this is a lot of adopted kids, I don't know, or maybe he just decided to go with names from different ethnic backgrounds. Lee has 1 child, and Lee's child is named Dante. And then Divjo has 4 children. Francois, Ursula, Tova, and Ezekiel. Now those, don't need 4 pieces. There we go. Ezekiel. And we're going to use a graph to represent this family. And so I imagine if you haven't made your own family tree before, you've at least seen one somewhere. So up here we're going to start with John. John is where it all begins. So John then splits off into 3 different parts here, to Jose, to Lee, and to Divjo. Those are his 3 children. So we're going to say that each person will be represented by a vertex in the graph, and then we'll split it off from there. So these 3 vertices, this would be Jose, this would be Lee, and this would be Divjo. Yep, the cold's still there a little bit, you can probably tell in my voice, or whatever that nasty thing was, but mostly gone. Feeling much more chipper today. And then Jose has 2 children, Crystal and Mohammed. So you can split off from Jose, split that off into 2 more parts. Let me spell that correctly. There we go. And Lee just has 1. So this one, it could go off in any direction, but you're just going to have 1 branching off from Lee. That would be Dante. Dante is Lee's child. And Divjo, we're going to have 4 different branches. I'm calling them branches. It's not really a technical term, but they're kind of, that's what they basically are. They're branches of this tree. We're going to talk about what makes this a tree, why this is a tree in graph theory. There's a very specific definition of that. So this is Francois, this is Ursula, this is Tova, and this is Ezekiel. And so that is it. That'll do it. Something like that, family tree, you would just branch off, split it off like that. Alright, so before we start example 2, I want to give you a couple of definitions. So we saw a tree. What is a tree though? What makes this a tree in graph theory? Yeah, it kind of looks like a tree. It's branching off in all these different directions. But we can't just say it looks like a tree, or it's kind of like what we see in a tree. We have to have a technical definition for it. So a tree, it is a connected graph We should know what connected graphs are from our previous lessons. So it's all connected. There's no vertices just hanging out by themselves or disconnected parts of the graph. But if you take any one of these edges away, you will then have a disconnected graph. That's what makes it a tree. And so we can say in which each edge is a bridge in the graph theory sense. So if we take any of these away, that would make a disconnected graph, that would make a disconnected graph, and so on. So we would have a disconnected graph if you removed any of those edges. And then a spanning tree, is a tree in the graph theory sense. It's a tree that is created, not a biological sense, botanical sense. Is that what I want to say? Botany. That is created from another graph by removing edges while still maintaining a path to each vertex. Okay, so that is the definition of a tree and a spanning tree. And we're going to check out a spanning tree, or an example of that in example 2 here. So example 2, determine a spanning tree for each graph below. This will actually be 2 graphs in one example. So for each graph below. So over here, I'm going to make my original graph, and then I'm going to put a line here to separate these over here. I'm going to be making my spanning tree. So I'm going to go from the original graph. I'm going to remove some edges while still maintaining a path to each vertex, and by doing so I will have created a spanning tree. And so let's say we start off with something like this. And remember, you have to draw these dots in. They're actual vertices. If you don't draw the dots in and just did something like that, there would be no vertex there. This wouldn't count. So I have to draw in the dots. And I'm going to say I have all those as vertices. This will be A, B, C, D, E, F, and G down here. And then on the other one, make kind of this large rectangle. You'll have 2 rows to it, and it will have 5 columns to it. So 1, 2, 3, 4, 5. And then each intersection is going to be a vertex. So lots of vertices in this one. Sounds like some people are working in the storage room in between the classes. If they get too loud, I'll go yell at them. But hopefully they'll be okay in there. We've got all these different vertices. Let's label them as you see here. So A through F on the top, G through L in the middle row. Oops, why did I write L? I'm not sure. I wasn't thinking. That's a J, K, L, and then M through R on the bottom. N, N, O, P, Q, and R. And so we are trying to create create a spanning tree. So right now, I don't want you to erase what I'm about to erase. I just want you to watch for just a moment here. Okay, so this is one possibility. I could erase BC. Getting rid of that edge, you're just watching right now. Don't actually do that, just watching. But if I get rid of that, I still have these all connected. So I could have gotten rid of this one, and B, C, and A would still all be connected. But I can't get rid of another one of these two now, because if I remove this one, I have a disconnected graph. So that's not going to work. So I'm going to put that one back. And I could take this, and I see this as an option. There were other options. I could have erased this one actually and been fine, but I decided to go with this one. And then over here, I decide that I want to go erase this one because I still have here. If I add that there, I have multiple ways to connect those points, but now there's only one way here, and every single edge that's left, this is the key part, the kicker, the most important part, every single edge that I have left here is a bridge. If I got rid of any one of these edges that are still remaining, I would no longer have a connected graph. And so it's a tree. This is a spanning tree because I got rid of edges that were in a connected graph originally and created a tree. And so I'm going to put those all back that I erased, but I'm going to draw what we had now over here. Is this the only way you could have done that? Definitely not. There's more than one way about that, and we're actually going to write down where you can check out some of the other ways that that could have been done, or so how some of no where they are. Yeah, that's good. Where they are in your book, that's where they are. So let's label these, keeping the vertices the same, labeled the same. So this is still A, B, C, D, E, F, and G. But now this is a spanning tree because we took the original graph, got rid of all the edges that we could to still have a connected graph where each edge now is a bridge. It's a spanning tree. Let's do the same sort of thing with this one. Okay, so now again, just listen here and watch and learn. Okay, so I'm going to get rid of this one. Was that the only one I could have done, or did I have to start with that one? No, I could have gotten rid of this one, and these would all still be connected, but this is just the way I decided to go with this. There's a lot of different possibilities here. So I'm going to get rid of that one. I'm going to go with that one gone. It looks like this is still a possibility. I could get rid of that one because this would still be connected there. I tried to have some fun with this a little bit and make it symmetrical. And so I got that there, and that gone there. I can get rid of, I didn't want to do that one. Sorry. I wanted to get rid of this one instead. If I got rid of both of those, that would be a disconnected graph. Q. Actually, no, it wouldn't. But if I got rid of all three of these, if I got rid of that one too, it would have been a disconnected graph. So I'm going to get rid of that one. And it looks like I still have this that I could get rid of here, or I could have gotten rid of that one. Both of those are options. I still have one more I can get rid of right here. I can do that. And now, do I have a tree? Do I have every single edge being a bridge? So if I removed any one of these edges, would it become disconnected? Yes, it looks like it would at that point. And so I'm going to recreate this over here and keep our original graph. So keep that there. Hopefully you didn't erase that, because I told you like 3 times not to erase that. At least 2. I suppose you could watch the video again and you could tell if I was being honest with saying at least 3. But if you can do that, I think you have too much time on your hands. Honestly. I'm just joshing you. I'm just kidding. Just messing with you. Just trying to make it interesting. Okay. So we've got 3 dots in each column, 6 dots in each row, and I'm going to connect them the way I had done before. And so it looked like this. Looks kind of like an H and maybe an O, a T. Pardon me, not exactly sure. But you may be able to even spell out a word like this. Kind of have some fun with it. Maybe it says Hoth or something like that. I'm not exactly sure. That'd be a very abstract looking word there, but let's put the labels on here again. E, F, G, H, I, J, K, L, M, N, O, P, Q, and R. Okay, and so with this in a different color now, I want you to do something like this because I want you to look at a couple more examples. So I would like you to pause the video, actually stop what you're doing right now and look at two more examples on there's actually two more examples for each on pages, or page 863. There we go. Two more examples for each is on page 863. So take a moment, pause, look at your book there, and just notice there's a couple more ways in the book that you could have drawn it. There's even more ways than that you could have drawn it. So it's not that this is only one. It's not that these would be the only three, mine and the two in the book. That's not the case. There's going to be a lot of different ones. Okay, so who is this guy? Who is this guy? His last name is Kruskal. I'm not sure if I'm pronouncing that correctly, but this is his algorithm. This is his methodology, his step-by-step procedure to allow us to construct a minimum cost, or to construct the minimum cost spanning tree. So that was another one of our definitions, I believe, back here. Yep, minimum cost spanning tree and Kruskal's algorithm. So here's the rest of what we had back there. So minimum cost spanning tree from a weighted graph. These are the steps you need to follow. So this is one of our definitions. I'll underline that little phrase right there. And I think it's actually pretty easy. I think it's fairly intuitive, but it's definitely worth writing down and having in our notes here too. So I'm going to have you write this down for me to select the lowest cost edge of the graph. Okay, so that makes sense. We would select a lowest cost edge, and that should be somewhere in the minimum cost spanning tree. And then next you would select, you might hear some kids walking around outside right now. I'm doing this during my prep period, and so hopefully they won't get too loud or say swear words and whatnot. Let's keep this G-rated, guys, okay? Thanks. So select the next lowest cost edge. That does not, or that doesn't, form a circuit. With the first edge. And we're going to do a problem where we go through these steps to help us solve a problem. So if you're like, I don't really understand what you're meaning by that, Mr. Wagner, you need to help me out more. Don't worry, help is coming, help is on the way. The next step, select the next lowest cost edge. That same thing, same idea, that doesn't form a circuit, but now not with just the first edge, but with both of them, with the previously selected edges. And then we continue this process. So at step 4, continue selecting the next next lowest cost edges that do not or don't form circuits excuse me, with the previously selected edges. And then finally, step 5, when the spanning tree is complete, guess what you have? You have what you're looking for. You have the, let's say the instead, you have the minimum cost spanning tree. Whoop whoop! Hooray! Hurrah! Hooroo! Hooroo! You have the minimum. Let me finish writing this before I get so excited. Minimum cost spanning tree. Yeah. Alright, so let's check this out in our final example for this one. And so we're going to say this is Palmcaster College. At a real place, not that I know of, I made it up. But we're going to pretend it is, and that this is what it looks like, even though this is actually the University of Michigan, best college in the world right there. I didn't go there, but that's who I root for. Go Blue! Go U of M! Dun, 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 dun. Alright. They are installing. Wait, what? Go Blue? Oh yeah. Let's make sure we get that in there too. It's installing an underground network on campus. So we're talking like internet network or a local area network, a LAN. They want to connect oh, I forgot to put that in here. Fiber optic. There we go. Fiber optic. So squeeze that in there somewhere. An underground fiber optic network on campus. They want to connect the entire campus. As cheaply as possible. Makes sense. Don't want to spend any more money than we have to get this done, but we want to make sure that it's done right and that we're actually all connected. Excuse me. The graph below is a weighted graph, so we're going to draw a weighted graph in just a moment, showing the distances we're going to say it's in meters between particular buildings on campus. Okay, and so let's start drawing our graph. And so I'm going to make this fairly large so that we have enough space to see everything and to see it easily. So all these vertices are going to represent different places on campus, and we're going to label them a little later. But just start by drawing the vertices in these approximate locations on your paper. I'm going to say this one's about there, this one's here, and then something like, I'll bring that one in a little bit, we're going to have a key over here telling us what each letter stands for. Excuse me. So let's connect all the vertices with edges as you see me drawing in here. So we're going to say these are kind of like the sidewalks between the buildings on campus, the fastest way to get from one building to the next. We're going to say there's a connection there as well. Keep drawing in those connections, those edges. Remember, graphs, you don't have to draw perfectly straight lines. So I could do that here. If you wanted to use a straight edge, it might actually be a little easier to draw those things in. But I am making this fairly symmetrical. There's just a little piece here missing. Okay. So all the dots are vertices. They're all buildings on campus, kind of like where the buildings are located. Generally on campus, I'll make sure I make those a little bit bigger so they stand out a little bit more. So all the edge intersections are actually where a building is on campus. Let's go with this being L. This is F. This is CO. I'll tell you what all these things stand for in just a moment. That's M. This is SC. Here in the middle we got CA. AD right there. This is going to be E. AT and ST. So you may be heading off to college soon, or you might actually be in college already if you're using this textbook at your school, at your college. And so let's label these buildings, or I already labeled them. What do they stand for though? CA is going to equal or be the cafeteria. So I'm going to put this as my key to what the buildings are. This is the cafeteria. And SC, this is the science building. M, oh yeah, gotta have a mathematics building on campus. That's a math building. AD stands for, there's AD, administration. So the heart of campus right there, the heart of how everything gets run on campus or at campus. AT stands for athletics. CO is going to be the communications building. There we go, communications. E is for English. F is a foreign language building. Foreign language. And we got two more. L is the library. Maybe spending a lot of time studying there if you're going to college. And ST is standing for student services. So maybe you need to get I don't know, you need to get some health. I can't even think right now. You need to have something checked up on, and you're on campus, and or you need to go join. You want to join a club or something like that. You might go to student services. So let's label these. It's supposed to be a weighted graph. It's not a weighted graph yet because I haven't drawn anything number-wise next to these. So each edge, this is representing the distance in meters for each edge, or between the building, one building to the next. There are some assumptions we're building into this. Like, are you saying, well, is it from the edge of the building to the edge, or the center to the center? We're going to say, don't worry about that. We're kind of simplifying this example a little bit here. Okay, so just assume it's from one building to the next, and don't ask any other questions. All right, this is 29. This is 25. Right here is 40. Right here is 50. This one 62. Down here 70. Over here this is going to be 74. Notice not drawn to scale. This one would actually be longer than this one, so none of this is drawn to scale. You can't trust the looks of the picture then. You have to trust the numbers that are actually there. It's 45. This is 38. This one's going to be 58. 65 up here. We got 30 from cafeteria to the foreign language building, and final language arts to foreign language, or not language arts, library to foreign language. 60, I missed one, library to cafeteria, that's 59. So is this now a weighted graph? Does every edge have a specific value attached to it? Yes, it looks like it does. And so now we are going to do, we got the setup done, now we're going to do the problem it's going to be asking for. So determine the shortest distance to link the entire campus. In other words, we're going to be finding the spanning tree, the minimum cost spanning tree for this. And so we don't need to connect fiber optics to buildings twice or 3 times. We're just wasting our money then. So we only need one connection between everything. We need everything to be a bridge, basically. If we remove any of them, then you're not connected. But I wouldn't want to have something here and here and then make another connection here, because they're already connected. They're already plugged into the network. No reason to reconnect there and there. Most of these networks are going like the speed of light or something very, very close to that. It's not really going to go any faster network-wise if you have another connection there. If things are going at the speed of light or close to that. So how can we do this? We're going to keep going back and forth between this and this. You'll definitely want your different color for this. I think that's going to make it a lot easier to determine. So we're going to, or a lot easier to look back on later and figure out what exactly we did. So using good old Kruskal's algorithm. So we first select, and in here I'm going to be writing it in a way where you read it later and you're like, oh yeah, that's what we did, that makes sense. So I select edge 1. We're going to be writing more here than you'll need to when you're doing the problems yourself. So this as labeled, and I'll say above even though it's on this previous page for me, because you're probably having this above what you already, or it's above what you're writing right here. So I'm going back here. It says to use this algorithm. So what are we supposed to do? We're supposed to select the lowest cost edge of the graph. Lowest cost can also refer to the smallest distance or shortest distance here. And so that's what we're doing here. We're looking for the shortest distance one. And so I'm going to use a highlighter for this. You can use just a pen or whatever, but I think it's just going to be a little easier to see what's going on here with a highlighter. And so I look at the whole graph. I'm looking for the lowest one or the smallest value of all of these. The smallest value is right here. So in your pen or with your highlighter, I want you to highlight or outline, overlap there. If you're using a pen, just do something like this and make sure it's really clear what you've gone over. This I'm going to put a 1 next to in my different color. That was my first edge that I chose because it was the lowest distance, the lowest cost. In this case, it's the lowest distance, smallest distance one. Okay, so from there, we continue to select the next shortest distance. That doesn't form a circuit with the previously selected edges. So that's like steps 2, 3, and 4 in Kruskall's algorithm, so we're doing that with previously selected edges. And we'll just say, see the colored numbers above. So we're going to refer back to our weighted graph, draw some things in there. I'll use a highlighter, but you can just outline it over in pen instead if you prefer to do that. But with the different colors, also including which one came first, second, and third. So next up, we're looking for Kruskall's algorithm says select the next lowest cost edge that doesn't form a circuit with the first edge. And so I look around here. I'm looking basically look for the next lowest number. The next lowest number is 25 right here. And so I'm going to highlight that. It's okay to use this one because this does not form a circuit with this one right here. And because I just did that one, this would be number 2. I'm going to continue doing that here on the graph now. So let's do the same thing on yours. So we're looking for, keep going in order, find the next lowest one. To me, I want to make that 9 a little clearer. There we go, that's a 9. Okay, so what's the next lowest one? So we got 24, 25. I don't see 26, but I do see a 27 right here. And this definitely does not form a circuit with the previously selected edges. So I'm going to highlight over that edge, and I'm going to call that number 3. So that was the third one. Keep doing this process. Keep going through this process. Look for the next highest one. Looks like that would be 29 over here. Am I right? I am right, yeah. Okay, so next here, it looks like I did this wrong on my other notes. Ooh. So next up would be 29. That's why it's good to double check your stuff. So does this form a circuit? No. If I connected this one now, that would then form a circuit. So this does not form a circuit. It just connects these parts. So this is kind of like the tree part now. I would need to get this connected eventually. But this one right here is going to be the 4th edge that I selected. And so now let's continue the process. We're done with 29, and let's see if there's any other 29s. Nope, doesn't look like it. So now let's look for 30s. There's a 30 right there. And so from there, I'm going to highlight that one. That's going to be our 5th choice then. So I'll get my pen. I'll label that with a 5 in the color there. Still don't have a tree yet, so I keep going. I don't have a tree for the whole thing, a spanning tree for the whole thing. 30s there, no other 30s. 31, nope. 32, yes. 32 right here. I can highlight that one because that doesn't form a circuit with any of these other edges. And this would be my 6th one that I've chosen. Keep the idea going. Let's look for what we got next. So I've got 30, looks like no more 30s except for right over here, 38. So this one doesn't form a circuit with the others. I can highlight that one or go over that one in my pen, and I would say that would be the 7th one I've chosen. And so let's keep going. I've got, oh, didn't want to do that. There we go. I've got 38, 39, no, 40. Yes, but here we go. So if we go here and we're looking at the Kruskall's algorithm, we could not be thinking very clearly, and we would just draw that and connect it, and then you say, oh wait, oh, I just made a mistake, because what happens if I actually connect this here, I now have a circuit. I can go start and end at the same vertex. This would be unnecessary. This would be a superfluous, totally unnecessary connection to make. You would be wasting your money making this extra one because you've already connected all these buildings together. This would just be unnecessary. And so we're not going to do that one. I'm going to have you, in your color, actually cross off that number. So that did come next, but we're not going to use that one. After 40, 41 right here would come next. But the same thing applies here. These are already all connected. Connecting these two isn't going to help you out at all. You've already got them connected. You're just going to be wasting your money again. So I'm going to cross that one out. We don't want to use that one. Now what would come next? We've got 45, it appears. 45, this, if I make that connection, that's not going to make a circuit at all. And so this would be one that I would want to connect. And it looks like we're real close. If I just could connect this part to this part over here, and then I have all my buildings connected. I have my spanning tree. And so this one is going to be the 8th one we've done, and then with what's left, 45, we've got 50 would come next. And so that does it. That connects everything together. Any other connections we make would make a circuit, and those would be, again, superfluous, totally unnecessary. They're all connected the way it is. This would be the cheapest way to go. So let's label this with a 9 right here. So it ended up taking 9 different connections. So if we're doing this, if we're actually putting this underground fiber optic network on campus, this is the best way to do it, or the cheapest way to do it, to make these connected in this way, because you're going to be spending the least amount of money, because you're going to have to be doing this. You're probably going to have to pay somebody by the meter to install this. And so let's write down, let's finish up what I have here, that we also, or we have also crossed out any edges, or any edge amounts, let's call it that instead, any edge amounts where connecting the vertices would create a circuit with the previously selected edges. Okay, so that's where we crossed off the 40 and the 41. And we didn't have to cross off the rest of those. We could have, but we already had a tree, so I just stopped there. But could you have crossed off this and this? Yeah, you could have done that. There goes my voice again. Excuse me. So, selected edges. And after edge 9, a tree has been completed. Connecting all the vertices. The vertices are representing the buildings. On campus. So the shortest distance is, and let's go back here and see what we got. So 1 through 9, I'm just going to refer back to this. Above them, let's put the numbers and circle them like we had in the drawing, just to make it easy to refer back and forth between these two parts. 6, 7, 8, and 9. Okay, so 1 and 2, that was 24, 25, and 3 was 27. So 24 plus 25 plus 27. 4, 5, and 6, we had 29, 30, and 32. 29, 30, and 32. And 7, 8, and 9 were 38, 45, and 50. 38, 45, and 50. So if we add all those things together, let's see what we get with that. So I'll take out my calculator to do that. And we got 24 plus 25 plus 27 plus 29 plus 30 plus 32, 38, 45, and 50. Let me just double check that I typed all that in right. Looks good to me, and let's see what that is. It's 300 exactly. So 300, and this was in meters, so don't forget your units. This would be in meters. And then we'll do a part B here. This is what it really comes down to. What's the cost of this? So if each meter of cable costs $565. Whew, that's a lot of money, but we gotta have this cable protected. It's gonna Costs a lot to dig up the ground. It costs that much to install. Determine. This is a highly sensitive cable, high-speed network here. Determine the total cost to link the campus at the lowest cost. So we've already done the smallest distance, so the lowest cost would correlate directly with that smallest distance. So to do this, our solution, all we'd have to do is take that number right there, 300, multiply it by 565, and that will give us the answer we're looking for. So 300 times 565, let's check that out. Let's see what that gives us. 300 times 565 is $169,500. So that's a pretty penny, but this is a big college campus. It's going to cost a lot of money to get that network up and running, but that's how much it's going to cost if this was all true. Hopefully you found that very helpful. I think this is very applicable to a lot of real-life application type problems. Pretty cool stuff, pretty neat stuff, I think. And thanks, Cruisecall, for the very clear, very intuitive, easy to understand algorithm. And in class, let me know if you had any questions. I hope you do well with this, and yeah, go at it. Trees, it's fun, exciting. See you guys.